junior year.
Oh, I'm so excited.
No, this is our first class, bro.
Good morning, ladies.
Hi, good morning.
Good morning. Welcome to physics.
Oh, yeah, great. Are we going to learn anything?
Oh, you're going to learn a lot of cool stuff. Like, for instance, you never really touch anything.
That's not true. Look. I'm touching the wall right now. Look.
Are you sure about that? Technically, you're not.
I wonder.
Hey, Brooklyn. What? I got something to tell you. What? What do you want to tell me? Oh my gosh, what? Stop touching me. Did you say stop touching me? Yeah, that was really annoying. Ooh, actually, friend, I'm sorry, but I actually was not touching you. You see, thanks to my handy-dandy diagram,
Oh my gosh,
I can explain to you that we are all made of atoms, and atoms have different rings of electrons. And the outermost ring is called the valence electrons. So, since I am made of atoms, and you are made of atoms, and the valence electrons make the outside of the atom negatively charged, we both have negative charges. So, when I tap you on the shoulder, I'm actually just repelling your valence electrons. I'm never touching you, so you can deal with it because it's just the electrons repelling each other.
Stop repelling me.
No.
Can we repel farther?
No, it's okay. I just wanted to let you know.
Yeah, no, thanks. True friend.
Whatever. Hey, Brooklyn. Yeah, I'm done. Can you take that to the sink for me?
Yeah, okay, sure.
What the heck? What?
Why would you punch me? What's going on?
I didn't punch you.
Pretty sure you did. I'm gonna have a bruise there to prove it.
No, I'm sorry. I don't have a handy-dandy diagram to explain this one to you. However, it's the same thing as last time. Since you're made of atoms, and atoms have valence electrons, you know the deal. You're covered in valence electrons, I'm covered in valence electrons, so we're really just repelling each other. What you're feeling is your sensory nerves detecting disturbance in homeostasis, right? So that sends a transmission to your pain receptors and then to your brain, and they're like, I'm hurt. But really, I'm still not touching you. Physically,
No,
I'm not touching you.
Okay.
I'm just, making you hurt a little bit, so.
Thanks.
But yeah, there you go.
Oh my gosh, why would you push me in the pool?
I didn't push you in the pool. I mean,
pretty sure you did. I'm actually really wet here.
well, okay, see, actually, when I pushed you in, all that it happened was the water was displacing you. That's all it did.
If the water was just displacing me, why am I wet?
Oh, well, actually, hold on, I have a diagram for that.
Oh gosh, give me all.
See, here in this diagram, we see that water is polar. It has a positive side and a negative side. Since you are covered in valence electrons, right, and negatively charged, we went over this part, you are getting the water on you, that's the positive side. And then carbon bonding, hydrogen bonding, all that stuff. But, yeah, so it displaced because two things can't be in the same space. So, physically, all that happened was you were taking up space that the water was, and so it had to move out of the way. But now some of it's bonding to you because you're negative and some of it's positive, so blah, blah, blah. So I'll probably push you later. Coulomb's law. All right, this is how we can explain how things attract and repel from each other. So we have F is the force of attraction or repulsion. K is Coulomb's constant, 9 times 10 to the 9th. We have Q1 and Q2, and those are the two charges of the things that are attracting or repelling. And then R is your radius, so R squared is what is going to be in the equation. And Brooklyn is going to explain what this means.
Okay, so since R is in the denominator, you know that as R gets bigger, the force of attraction or repulsion is going to actually decrease. And so if both charges, Q1 and Q2, are negative, then this is going to be a force of repulsion. And if Q1 and Q2 are different forces, so one is positive and one is negative, then you know that the force is going to be a force of attraction.
All right. Example of how to use Coulomb's law. So here are your units and your measurements right here. So you have Q1, the charge of Q1, the charge of Q2, and the radius. So we have the formula over here. So let's just write it down real quick. So we have the force is going to equal K, which is the Coulomb's constant, 9 times 10 to the 9th. And those measurements are in C and meters squared. And then this is going to be 2.5 times 10 to the negative 6th. And over real quick. Coulomb times 4.3 times 10 to the negative 6th coulomb. And all of that is over 0.04 meters squared. So that's just filling in all of the variables with the numbers that we were given. So now you can get rid of meters squared, and this is also squared, so you get rid of those. And now you're left with 9 times 10 to the 9th times these 2 units divided by 0.04 squared. So when you multiply those all out, you get F equals about 60 newtons. So that's going to be your force between those two charges.
Camille.
You have to say, stop touching me.
Oh, that's true. I did have to say that. Kind of the whole point.
What do you say?
Okay.
Fail.
You're a fail.
Brooklyn is looking ratchet.
Hey, I didn't want to put makeup on because I had to get wet.
Right, barely, whatever.
Whatever.
You should jump too far.